Welcome back. Today we're finishing up with section 10.4 on polar coordinates. And of course with that, polar graphs. So the idea here is that we still have an origin, and that's our polar axis. We have some angle theta and some radius r, and between r and theta, that identifies a point in the plane. So this is really just a different way to identify ordered pairs. Instead of left and right, up and down, we have an angle and a distance to identify a point. So the relationship between polar and rectangular about the origin's in the same spot. So if I were to sort of drop an xy plane over this, if this point is at xy in rectangular, here's x, here's y, so you can see that x squared plus y squared equals r squared. You can see that cosine of theta is x over r, and that sine of theta is y over r. If you want to solve for x or y, x then would of course be r cosine theta, y would be r sine theta. Another useful relationship, if you consider the tangent of theta, sine over cosine would simplify down to y over x as well. So those are some useful ways to translate between rectangular and polar. So in rectangular, this point would be called xy. In polar, we would identify it as r theta, the radius and the angle. Alright, so let's look through a couple quick examples here. So if we're given r theta, so the polar coordinates as 7 comma pi over 6, we can then also identify the rectangular coordinates. So x is equal to r cosine theta. So our radius here is 7, so 7 cosine of pi over 6. So pi over 6, 30 degrees, cosine of 30 degrees is root 3 over 2, so we have 7 root 3 over 2. And y is r sine theta. So 7 sine pi over 6, sine of 30 degrees is 1/2, so y is 7/2. So our rectangular coordinate would be 7 root 3 over 2, comma, 7/2. And if I do just a quick sketch in polar coordinates, we can see that this would fit. So if we I'll emphasize what would be the y-axis and what would be the x-axis in the rectangular mode. These are broken into, I believe, 15-degree increments. So 30 degrees and a radius of 7. So 1, 2, 3, 4, 5, 6, and so 7 would be just a little bit off. So we're in Q1 as expected, positive, positive. And it does seem to fit about 3.5 units right. Or, my apologies, 3.5 units up. All right, we can also work with negative radii. So if we have negative 5 pi over 3 in polar, and we want to go to rectangular, x is equal to negative 5 cosine of pi over 3. So pi over 3 is 60 degrees. Cosine would be a half, so negative 5 halves. And y equals negative 5 sine of pi over 3. Sine of pi over 3. Sine of 60 is root 3 over 2. So y is negative 5 root 3 over 2. So those would be our rectangular coordinates. And if you look at just a quick rough sketch again, you can see kind of how that makes sense that we end up in Q3. So pi over 3, so 60 degrees. So here's 30, 45, 60. And then a radius of negative 5 basically means instead of going up and to the right, then we're going down and to the left. So then going 1, 2, 3, 4, and 5. So we're right down here. So negative, negative, it does fit that we're in Q3 based on the angle and the fact that the radius was negative. So instead of moving up and right, down and left. All right. So have you try a couple out. So I'll give you a few polar coordinates and see if you can turn them into rectangular. So we'll do, let's see, let's try a 2 negative pi over 2. Turn that into rectangular. When you finished with that, try 2 and 3 pi over 2. And if you finish that, negative 2 and pi over 2. Go ahead and just pause the video real quick. See if you can figure out the rectangular coordinates associated with that. Okay, welcome back. We'll just put these all on the same grid here. Okay, so our first one, radius of 2, angle of negative pi over 2. So instead of going up to pi over 2, we're rocking back to negative pi over 2. And then we're going 1, 2 units out. So x, 2 cosine of negative pi over 2. Cosine of negative pi over 2, though, is 0. So 2 times 0 is 0. Y is 2 sine of negative pi over 2. Sine of negative pi over 2 is negative 1. 2 by negative 1 is negative 2. So 0, negative 2 in the rectangular. All three of these were polar. Our second point, we went to 3 pi over 2 and a radius of 2, and notice we landed on the same point, and the math does bear that out. X is equal to 2 cosine 3 pi over 2, which of course is 0. Y is 2 sine of 3 pi over 2. Sine of 3 pi over 2 is negative 1. 2 by negative 1 is negative 2. And we still have our 0, negative 2 in rectangular. And this last one, not super surprising based on what you saw in the first two. I'm showing you that there's, yes, another way that we can land on exactly the same rectangular coordinates. with different looking polar coordinates. So we went to an angle of pi over 2, but had a radius of -2, and sure enough, that knocked us right back down there. And you can fill in the math on your own on that last one. You'll still come up with 0, -2 on that one as well. So one thing from there that we learn is that the polar coordinates are not a unique representation. So in rectangular coordinates, the representation is unique, aside from, of course, if you want to go decimal of proper fraction, things like that. Generally, it's considered unique. Polar coordinates are not unique. You can really have kind of an infinite number of representations of the same point. Going rectangular to polar, we use the relationships that we talked about back in the first couple pages. So if we have 5, -5, and I want that to turn into polar, recall that tangent theta is y over x. So tangent theta for this is -5 over 5, which is -1. So if tangent theta is -1, there are multiple places where this happens. Tan theta being -1 just means sine and cosine have opposite signs. Well, basically that means up here or down here, either in Q2, where cosine's negative, sine is positive, or in Q4, where cosine's positive, sine is negative. And there we just use which quadrant the original is in. So since this one is in Q4, we're talking about this angle. So that's 1 pi over 4, 2, 3, 4, 5, 6, 7 pi over 4. So again, even though that's not the unique one, and I could add 2 pi to that and get the same angle again, and 2 pi again, another new angle, an infinite number of ways to represent it. But this is sort of just the cleanest angle. And then we go with finding the radius as well. Well, x squared plus y squared is r squared. So we have 25 plus 25 is r squared. So r squared is 50. So r is 5√2. So then our polar coordinate for that point would be radius 5√2, angle 7 pi over 4. Again, not necessarily unique, but we tend to try to go with the simplest one. All right, so then we get to play with some polar graphs. We'll start with just r equals 4. Just what it sounds like. If r equals 4, well, x squared plus y squared is r squared. Well, this is a circle centered on the origin. With a radius equal to 4, hence start saying r equals 4. So on this one, we're just sketching a circle with the radius of 4 units. So here's 1, 2, 3, 4 units out. So there's our graph of r equals 4. Circles aren't the only shapes that we run into, though, in polar graphing. They might tell us theta is 3 pi over 4. Well, since we know theta, we use what we know about tangent theta. Tangent theta is y over x. So tangent of 3 pi over 4 is worth y over x. Tangent of 3 pi over 4 is 1. So 1 is y over x, so y equals x. So we have basically the identity function. -1, my apologies, y equals -x. So here's our overlay of the rectangular coordinates. So y equals the opposite of x, so 3 pi over 4, so 1 pi over 4, 45-degree angle, 2 pi over 4, which is pi over 2, 3 pi over 4. So here is our graph. So we just have a linear function. They may give us one of r equals 6 cosecant theta. Well, I like to kind of see them with sines and cosines, so I usually take one step and just rewrite them that way. So r is 6 over sine theta. So 6 is equal to r sine theta. Well, remember our definition at the beginning, y was r sine theta. So that means y is equal to 6. So on this one, we have a horizontal line, so this one would actually be easier to represent with just our regular XY plane. So here is, we're at 1, 2, 3, 4, 5, 6. And we'll pretend that I can draw a straight line without a ruler. So there's our r equals 6 cosecant theta graph. Now we do have some other interesting shapes that come up with these. One of them is what's called a rose curve. So we'll start with r equals 2 cosine of 2 theta. We'll look at a quick little chart and then we'll fill the rest in with a calculator. So here's our theta and our radius. Theta is 0, cosine of 0 is 1, 1 by 2 is 2. If I go to, we'll go by 30 degrees each time. So radius then is 2 cosine of pi over 3. So don't forget we have this 2 here. Cosine of pi over 3 is half, so I have 2 by a half, which is 1. If we go with pi over 3, 2 cosine of 2 pi over 3, and cosine of 2 pi over 3 is a negative 1/2. 2 times negative 1/2, negative 1. And we'll go to pi over 2, and then we'll let the calculator do the rest of the work for us. 2 cosine of 2 times pi over 2 would be pi. Cosine of pi is negative 1, 2 by negative 1, negative 2.